Hello, and welcome to Math with Mr. Bill. I'm Bill Anderson. Today we are going through a series of problems to help one of my students get ready for a final. This comes from his second midterm, and this is problem number 5. Here we're asked to take a function and rotate it about the x-axis and find the volume of the function between x equals 1 and x equals 2. So with any rotation or volume, finding the volume by rotation problem, it's always a very good idea to look at a picture of this and get an idea of what we're going to be find the volume of. And this will also give us an opportunity to know which formula we're going to be using, whether it's the washer disk method or cylindrical shell method. So let's graph what we have here. And I just put in a couple of points. So if I plug in x equals 1 into that, I get 5 over the square root of 4. It's 5 over 2. So that's 2.5. And then if I plug in 2, that's 5 over the square root of 2, which is just less than 2.5. And we get a nice curve here, just like that. Nothing too fancy. Okay, so I'm going to repeat that down here. Now the next question is well, what method am I going to use? Am I going to use cylindrical shells, or am I going to use washers? And the rule is that if the independent variable of your function and the axis of rotation are the same, then you would use washers or disks. And so that's what we have here. We have the function is in terms of x, and then our axis of rotation is horizontal. It's an x-axis center of rotation. So we're going to be using the washer method or the disk method. Everybody calls it either thing. That would really, the disk method is just the washer method with the inner radius equal to 0. So the volume for this is going to be equal to the integral from one place to the next times, or of, the area of circles, because that's what we're doing, is we are adding up the areas of the circles. We're integrating over the areas of the circles. And to find that, that's pi times the radius squared. Okay. And since we know we're in the x direction, I'm going to go ahead and put this as dx. So the next big question is, well, what is our radius? And our radius is the distance from the center out to any representative circle. And so in this case, I can just put the center right here, like this. There's our circle. And our radius is given by the function. Literally, the radius is f of x. So it makes it real nice and easy this time around. And so let's fill in everything. So we have the volume is equal to the integral from the left side, 1 to 2, of pi times our radius, which is our function, 5 over the square root of x plus 3, squared, dx. So now we just need to integrate that. We've got don't have to worry too much about the drawing now. We've got all that. And we just need to work through the integration. So let's start cleaning this up a bit. We get, go ahead and take the pi out front and the integral from 1 to 2. And we have 25 over the square root of x plus 3 squared, which is just x plus 3 dx. And the 25 can come out front. Let's grab that out there. 1 to 2 of 1 over x plus 3 dx. Okay, so now we need to integrate that. And that should be fairly straightforward. The integral of 1 over any linear term is just generally the natural log of that linear term, especially when you've got the linear term with a coefficient of 1. So this is 25, oops, I forgot the pi. 25 pi times the natural log of the absolute value of x plus 3. And then we'll evaluate that from 1 to 2. Now I can get rid of the absolute values because neither 2 nor 1 are going to make the x plus 3 term 0, or a negative. So that's going to be 25 pi, and then in parentheses, the natural log of 5, plus, nope, not plus, minus the natural log of 4. Okay. Clean that up one last time. 25 pi times the natural log, and since we've got subtraction between two logarithms, we can turn that into division. So that's the natural log of 5/4. And that's it. That's our volume. So thank you for watching all the way up to this point, and I will see you in the next video.